So in this video, we're going to apply what we have looked at previously to look at the shape of electric fields due to more than one charged object. Okay, so electric field strength is also a vector quantity, and therefore we can also look at the superposition of the electric field. So we can work out the electric field due to more than one charge, just in the same way that we looked at the superposition of a charge in the earlier example due to two other charges. So we had a scenario with three charges. So let's just think for a sec. If we were right in between these two electric fields, and I'll just make my pen a bit smaller, from the positive, this is always a positive test charge, so from the positive it would be being pushed towards the negative it would be attracted. So the electric field strength at this point here would basically go straight across here. If we went to a point, say, up here, and we'll do a point down here as well, due to the positive charge, basically it's going to be being repelled in both cases, and due to the negative charge, it's going to be being attracted. So if we add those two together, we can see we get a vector that goes that way, and a vector that, hang on a sec, and a vector that goes that way. And if we did that all along that line, we would see we would get an electric field line that looks like that. Make sure that meets at 90 degrees. And, we could pick some other point maybe up here. It would be being pushed away like that from this one. And the negative, but it would be weaker because the distance is greater, would be going like that. So the net effect would be that we end up getting something that looks like that. Okay, and we could keep going. I won't show the working for all of them. Show that the electric field shape due to an isolated positive and a negative charge would look like this. So remember, the arrows always go towards the negative. It's the direction of the force experienced by a positive charge and away from the positive, like such. Now, we do a similar activity with, say, two positive charges. Well, if we go to this point right in the middle now, we would see there's no force on that point directly between the middle of the two charges. So right here, equal distance to both charges. Basically, the force is going to cancel out. So there's going to be no electric field right in the middle. So the force is going to be quite weak. If we want to think about, say, a point up here now, well, due to this one, it will go that way. And then due to this other positive charge, it'll be going that way. So if you like, we're going to almost, at that dead center point, have the electric field being the net of those two going up like that. So you could go through and look at all the points, and basically what you find is you get an electric field shape due to two positive charges. I'm just going to draw that a bit neater. That looks like this. And they're positive, so they're all getting pushed away. So just finish this one off. That one's a bit wonky, but you get the idea. And a negative field looks exactly the same, but everything is in the opposite direction. anti-parallel, as we say, so they're all getting pulled into the middle when we start to put the direction in. So I think you tend to, once you do these a few times, remember them. But if you ever do forget, you can go back and do that little vector type thing that I did just there to work them out again. So everything coming in towards the negative. So there we have it. We have the electric field due to two opposite charges, two opposite, and two with the same, because there's two possibilities there. So that is the first part of superposition of electric fields. We're going to now look at some more complex examples. Okay, so now we're going to look at, we're going to draw the electric field due to an infinite conducting plate of positive or negative charge. So we've got our infinite positive plate here, our infinite negative plate. We're then going to use the principle of superposition to draw the electric field due to two infinite parallel conducting plates with equal and opposite charges per unit area. And we're going to look at the field between, sketch the electric field between and near the edges of two finite oppositely charged parallel plates. So I'm going to do this one combined, because what happens here in the middle basically represents what would happen between two infinite plates, and we'll show on the edge what happens with our edge effects. So, positive plate, if we think about our test charge, it's always going to get pushed away because we do a positive test charge. And if we have an even distribution of charge through that plate, we are going to get a uniform electric field in the region surrounding that plate. So it will look basically like what we have here. So there's our positive due to an infinite positive plate. We can see the electric field is, if you like, uniform, that the lines are equally spaced in that space surrounding it. And the negative one obviously looks very similar. However, in this case, not going really well on my line spacing there, but I think that'll do. The field is directed towards the plate. So, if we go to two oppositely charged plates, if we think about a spot here in the middle, it's going to get pulled towards the negative, repelled from the positive, so it's going to be directly downwards. And in the space between those plates, that will be uniform. So it will basically be this even spacing. So we'll actually do a prac with an electric field due to a positive and a negative plate shortly. And you'll basically be firing an electron into an electric field. Now what happens around the edges is that we get some bending. So right on the corner it would come out at 45 degrees to the tangent, 45 degrees to that surface. So you would get these sort of edge bending out effects at the edge, which is what it's talking about near the edges of two finite oppositely charged plates. So hopefully we've covered those three intended student learnings there. So now we're going to look at the electric field that results when a solid uncharged conducting sphere is placed in the region between two oppositely charged parallel plates. So this scenario here. And we can apply a lot of the principles of superposition and charging that we've already talked about. Firstly, even though this charge is unsphered, this sphere is uncharged, we can think about it's still going to be made of positive and negative charges because it's made of matter that's made of protons and electrons, etc. So we can imagine that the positive parts will get attracted towards the top because that's negatively charged, and the negatively charged bits will get attracted towards the bottom because that's positive charge and opposites attract. So there won't be a net charge. The amount of positive and negative charge will be equal, but we'll get like the induction causing that sort of charge separation. And then we can think about this just like we think about the other fields. So if we were just at this point here, positive test charge, repelled by the positive there, pulled towards the negative. Here, positive test charge, repelled by the positive towards the negative. For out here, repelled by the positive and then pulled towards the negative. Remember, as it says at the top, always lines meet the surface, either of the plate or the sphere, at right angles, at 90 degrees. So we get this sort of thing going on, and then if we're over here, we're going to get a little bit of pull towards that. So we get something like that. And gradually the effect of that pull towards that gets less and less. So if you got sufficiently far away from that sphere, it wouldn't really have any significant influence in the middle. So the lines would become parallel again. I'm not going to worry about drawing the edge effects. We talked about edge effects in the last diagram. Next, let's look at the electric field produced by a hollow spherical charged conductor. This scenario here, and we'll just do a positive, we won't worry about doing the negative as well, and sketch the electric field that results when a hollow spherical uncharged conductor, here, is placed in a region between two oppositely charged plates, here. So let's think firstly about what happens inside this conducting sphere. And essentially, if you think about any point in here, basically positive test charge, the charge on this side is going to be pushing it, if you like, over this way. This one will be pushing it that way, so to speak. But these ones on this side will be pushing it back. So basically it's getting pushed from all directions. Yeah, the push from this one will be stronger because it's closer, but there's more charge over this area that's pushing back. So the net effect is that you get left with no electric field inside a charged conducting sphere, hollow charged conducting sphere. If we think about outside, well, it becomes just like our point charge. So here, positive, it's going to get pushed up. So we're going to get left on the outside with something that just looks like the point charged. So the outside, just like we've done before, inside the conducting charged spherical, hollow charged spherical conductor, there's no field. With this case here, it's really just like the case above. Once again, you'll get this sort of charge separation. I've done this the opposite way around this time. So the negative will get pulled up. There'll be no net charge because there's the same amount of positive and negative charge. Now, if we go to this point here, positive charge will get pushed down. Same there. And once again, we end up with something that looks like what we had in the case above. It's a bit wonky, but you get the idea. Once again, I'm not going to worry about the edge effects. We saw them on the previous slide. So that's 3 more scenarios that we need to think about the shape of electric fields.